So now what we want to consider is what happens when we start to put substituents on a cyclohexane ring. In some cases, those are going to be very small substituents, such as this first example with a methyl, or we'll look at much larger substituents as well. But basically the question is, does a substituent care whether it's in an axial or an equatorial position? So a group like this methyl group could be axial, or it could be equatorial. Now, right now, we're not going to worry about whether it's pointing up or down. That's something we'll concern ourselves with in a little while. But it turns out for something such as a methyl group, there's a 1.75 kcal per mole energy difference. And that probably doesn't sound like a very significant difference. And realistically, it's actually a very small difference. But if you remember back to general chemistry, you learned delta G is equal to minus RT ln of the equilibrium constant. And so if we know the energy difference, we can, get that to correspond to some sort of equilibrium ratio. And the ratio here is that the equatorial is favored by almost 20 to 1. So at any one given time, if we have methyl cyclohexane, approximately 95% of it will have the methyl group equatorial, and about 5% will have it axial. Why the difference? Well, let's look at their Newman projections. So the first one is going to be our axial. And then on the right, we'll put it what happens when it's equatorial. So when it's in an axial position, it will look something like this. And this is something you can also do with your models to follow along. And the equatorial will look very similar, except for the position of that methyl group. And the big difference that you see is that in the axial position, this methyl group, and again, this is another reason that it's good to follow along with your models, but that methyl group has a gauche interaction with this carbon here, as well as this carbon. A gauche interaction is worth approximately 0.9 kcals per mole. And since there's two of them, that gets us to approximately 1.8 kcals per mole, which is essentially the difference that we said there was between the axial and equatorial conformations. When the methyl group is over here in the equatorial position, the two adjacent groups are both hydrogens. And because those are both hydrogens, there's no gauche interaction for that methyl. And that provides our energy difference. So in general, for most substituents, because of these types of interactions, it's much more favorable for a substituent to be equatorial than to be axial. And as the group gets larger, that energy difference increases. So we just did CH3, 1.75 kcals per mole. And a ratio of about 19.5 to 1. If we make it just a little bit bigger with an ethyl, turns out the ethyl doesn't have a huge difference in energy compared to the methyl, only about 21 to 1. And a propyl group, a little bit bigger yet. Energy difference goes up a little more. Now we get up to about 40 to 1. But it's when we start to get to things like an isopropyl group. Isopropyl is a lot bigger. We're now up in the neighborhood of 86 to 1. And finally, with a Tert-Butyl group. If you want to see the differences, how these behave, probably the best thing to do is to, sort of put each of these groups together and put them on your cyclohexane chair conformation and look at how much steric hindrance is caused by the methyl versus the ethyl versus the isopropyl and Tert-Butyl. The isopropyl gets us up to 5.5 kcals per mole and a ratio of almost 12,000 to 1. In fact, you may read in some places that they say that the Tert-Butyl group is so big that it's essentially never in an axial position. All right, so from here, where we want to go is, if we're looking now at a cyclohexane molecule, how do we put it into its most stable chair conformation? And there's often two determining factors. One is if you have a lot of groups that are the same size, then you want as many of them to be equatorial as possible. The other way you might determine it is if you have a very large group, such as the isopropyl, or even better, the Tert-Butyl group, then you know that that group has to be equatorial. And once you place one group in an equatorial or an axial position, that sets you up for the rest of the ring. And let me explain how that works. So we're going to start using wedges and dashes a lot more often going forward to represent many of our drawings at this point. And the way we want to represent these, at least for cyclic molecules, is if we have a wedge, that means it points up. And a dashed line is going to mean it points down. Now, of our 12 substituents, our 6 axial and 6 equatorial, which ones are pointing up, which ones are pointing down? Well, with the axials, it's probably straightforward. That's pointing, that one's pointing up from the ring, that one is, and that one is. But so are these 3 equatorial ones. They're also pointing up. They don't have to point straight up, just basically up from, essentially the plane of where the ring is. The other 6 substituents all point down. And so that's what we're going to use as the basis for doing some of these. So let's say that I told you to draw the most stable chair conformation for this dimethyl cyclohexane, where both substituents are pointing up. So first question, where do we start? Well, the easy answer is we can start anywhere. I typically start over here at the bottom right. I'm going to label this as carbon 1 corresponding to 1 here, and then 2 here, and because there's no other substituents, I don't need to worry about the other positions. But let me go back and grab this drawing so that we have it. So on that first carbon, I have a methyl group that's pointing up. And on that first carbon down here, a group that's pointing up is equatorial. Now on the next carbon, I have another group that's pointing up. But on the next carbon, a group pointing up is axial. And so that's going to be our most stable conformation. There's no way to make this one so that both groups are equatorial. So let's do another one now. So I'm going to number these. And let's go get our drawing again. So at carbon 1, we have a group pointing up. That's equatorial. Carbon 2, we have a group pointing up. That's going to be axial. 3 has just hydrogens. And 4 has a methyl pointing up. So we've now drawn this. We have 2 axial and 1 equatorial. So what if we tried to do this a different way? So now, instead, I'm going to make this carbon number 1. Because remember, I can start anywhere in the ring that I want. If I do that, carbon 1 has a methyl going up, that's axial. Carbon 2 has a methyl going up, that's equatorial. And carbon 4 going up is also equatorial. So which one is better? Top one has 2 axial, 1 equatorial. The one at the bottom, where all my bonds seem to have disappeared, has 2 equatorial and 1 axial. More equatorial is better, and so this would be our most stable chair conformation. So again, to summarize what this part has said, if all of our groups are the same size or approximately the same size, then what controls everything is getting as many of them equatorial as possible. But sometimes it's controlled by a large group. So what if we said to draw the most stable chair conformation for this? So again, what we want to remember is that a group that's large, like that Tert-Butyl group, that Tert-Butyl group always is going to be equatorial. It's also, we notice, pointing up. So I'm going to choose an equatorial position that points up. Then if I start around the ring, our second carbon has a methyl pointing up, third one methyl pointing down, fourth one methyl pointing down. And again, it doesn't matter as much how many are equatorial versus axial, but that the largest group that we have is pointing equatorial. So again, as you start to do some practice with these, 2 main goals that we're trying to achieve. One is that we want as many groups equatorial, and second, we want the largest groups equatorial.